Welcome to Differential Equations. Today we're going to be continuing our discussion of Laplace transforms. This is section 7.2 in the textbook. Now, last time we were given the definition of the Laplace transform. We know that the Laplace transform of f, a function in t space, is defined as being the integral from 0 to infinity of e to the negative st times f of t dt. And provided that f is sufficiently well behaved, it doesn't grow too fast to overpower this exponential decay, then we observe the following transformations. The Laplace transform of 1 is 1 over s. The Laplace transform of t is equal to 1 over s squared. And the Laplace transform of e to the negative 3t is equal to 1 over the quantity s plus 3. And we would like to have some way to say, well, if I know the Laplace transform of a function is 1 over s, then I know that the function that you had to start it with, the function in t space, if you will, was 1. Or if you started with a function, took the Laplace transform, and you got 1 over s squared, then I know the original function that you had was t. And the same with 1 over s plus 3. I know the original function was e to the negative 3t. That would be nice. Unfortunately, we don't have a real convenient way of doing this. I mean, we've never really talked about a good way to undo a definite integral, even an improper definite integral. So we're left with our fallbacks, which is really one of our strengths, and that is pattern recognition. When we first learned about antiderivatives, we didn't really learn how to undo a derivative, right? We just learned how to recognize patterns. Oh, that's a power function, so you must have ended up subtracting 1 from the power and multiplying by it, so we're going to undo those. The same idea here. I don't really have to be able to undo this Laplace transform so much as recognize that if you tell me you started with a function and took the Laplace transform of that function, then the function, and the Laplace transform that you got was 1 over s, then the function you had to have started with was 1. There's no other option. And in this way, we're going to define the inverse Laplace transform. The inverse Laplace transform is going to be our way of going from S space back to a T space. So the inverse Laplace transform of 1 over S squared is T. And the inverse Laplace transform of 1 over the quantity S plus 3 is e to the negative 3t. And we rely not so much on our procedural ability here, our ability to actually undo something, so much as our ability to recognize, oh yeah, I saw that function before and I took its Laplace transform and I got it. So I can then reverse engineer it. We can generalize these somewhat. In the same way that we generalize the Laplace transform, we can generalize the inverse of the Laplace transform. If I were to ask you for the inverse Laplace transform of n factorial over s to the n plus 1 power, we saw last time there was a function that gave us this, and it was t to the n. So we can say that the inverse Laplace of n factorial over s to the n plus 1 is t to the n. We can say that the inverse Laplace transform of 1 over s minus a is e to the at. We can say that the inverse Laplace transform of k over s squared plus k squared is sine of kt. We can say that the inverse Laplace transform of s over s squared plus k squared is cosine of kt. And we haven't added anything new here. We just sort of acknowledge or come up with a notation now to use to say, okay, I'm undoing the Laplace transform. I'm going from a function in S space to a function in T space. And it's worth noting, if I want the inverse Laplace of some constant times the Laplace of f plus some other constant times the Laplace of g, that because of the linearity of integrals, this is alpha times f plus beta times g. That is, constants just tag along for the ride. I can break it across addition and subtraction. And so I'm, at the end of the day, I just come down to undoing the Laplace of f and the Laplace of g. So let's look at some examples. If I were to ask for the inverse Laplace of 1 over s to the 7th. Now, we've never taken the Laplace transform of a function and gotten 1 over s to the 7th. But using this generalization here, I acknowledge that if I rewrite this as Laplace, inverse Laplace of something over s to the 7, I'm looking for this n plus 1. So if I siphon one of those off, make it 6 plus 1 instead of 7. So that's s to the 6 plus 1 power. Now n is 6, so I need a 6 factorial up here. Of course, I can't just arbitrarily multiply by 6 factorial. I need to also divide by 6 factorial, but that's just a constant that comes along, that comes out. Tags along for the ride. And now, even though I've never actually taken the Laplace transform of a function and gotten this, I can say that if I had, that function would have had to have looked like t to the 6th over 6 factorial. I want the inverse Laplace of 1 over s squared plus 7. Pause the video for a second if you wish. Try to find the function that I started with in T space that gave me this. Now, none of my functions gave me 7, right? I never had a function in T space that I took the Laplace transform and it gave me 1 over s squared plus 7. That never happened. But I do see here I've got this same form. I just need it to be s squared plus k squared, and I need a k in the numerator. So if I take a beat and rewrite this as s squared plus root 7 squared, I'm almost where I want to be. Right? I haven't changed anything about it except perhaps what color it's painted. But I need not just s squared plus k squared in the denominator, I need k in the numerator. K here is root 7. So continuing this manipulation, I can put a root 7 in the numerator. That equates to multiplying by root 7. I can't just randomly multiply by root 7 unless I also divide by root 7. Thankfully, those constant multiples can just tag along for the ride. And now I have something that I can look back on and say, oh, that is a k over s squared plus k squared with a constant multiple tagging along. So I am looking at sine of kt, where the parameter k here is root 7. So this becomes 1 over root 7 times the sine of root 7 t. Next up, we have negative 2s plus 6 over s squared plus 4. So I had some function originally, and when I took the Laplace transform of it, I got negative 2s plus 6 over s squared plus 4. And the question is, what is the original function that I started with? What is the function in t space instead of s space? And I've never seen anything like this, right? I've got s squared plus 4 in the denominator. I like both of these. Both of these have an s squared plus k squared in the denominator, but you'll notice the numerator on both of these are both just one term. One has an s, the variable, and one has k, the parameter. I have both s and k here. Thankfully, our algebra skills are pretty strong, and we can break this apart. Since there's an addition sign in the numerator, I can break it across that addition. And now each part of this is something that I have hope for. I have s squared plus 4 in the denominators of each. The numerators on both are just a single term. They're just not the term I wanted. If s is in the numerator, I need it to be just s in the numerator. So any constants have to come out. Negative 2 is hanging out here. It's messing up the work. It's messing it up. So I'll pull the negative 2 out. And I'm going to rewrite the 4 as 2 squared so we can see it more clearly. Here, I've got a 6 in the numerator. The rule I want to invoke requires k in the numerator. K here is 2. So I need a 2 in the numerator. So 6 is 3 times 2. So I'm going to break 6 into 3 and 2. And so in this way, I now have two functions that I know the inverse Laplace over. I know what functions I started with to get this Laplace transform. S over s squared plus 2 squared is cosine of 2t. And 2 over s squared plus 2 squared is sine of 2t. And so we were able to, even though we've never seen this function before, by relying on our skills with algebra, we were able to turn it into some Laplace transforms that we know. Let's do a couple more examples. So I want to know what function, when I take the Laplace transform, gives me s squared plus 6s plus 9 over s minus 1, s minus 2, s plus 4. And we're perhaps fundamentally unhappy with this problem. Because not only do I have quadratic in the numerator, none of my functions have given me a quadratic s in a numerator. But also, I have a cubic in the denominator. None of my functions have given me cubics in the denominator. So I am perhaps fundamentally unhappy with this. And I've been kind with this example in that I already factored the denominator for you. That's a hint as to where to go with this. We know that polynomials can be factored into some combination of linear and quadratic terms. Here I've factored this into its linear terms. We also know this is a proper fraction. It's degree 2 over degree 3. This is a proper fraction, which means I can write this as something over s minus 1 plus something over s minus 2 plus something over s plus 4. This is our partial fraction decomposition. I just need to find the values that go in these numerators. In algebra, we would have called them, probably when we were learning this approach, we probably would have called them capital A, capital B, capital C, and then set up our equation so that this fraction is equal to the sum of these fractions. So just some small scratch work to give you a jumping off point if you need it. I'm looking to find the values of a plus b, or a, b, and c, so that s squared plus 6s plus 9 is equal to a over s minus 1 plus b over s minus 2 plus c over s plus 4. Which means that s squared plus 6s plus 9 has to equal a times s minus 2 times s plus 4 plus b times s minus 1 times s plus 4 plus c times s minus 1 times s minus 2. And then we solve this for a, b, and c. If I multiply everything out, there's some combination of a, b, and c, which give me 1s squared, 6 s's, and 9 units. Solving this actually tells me that a is negative 16 over 5. B is 25 over 6. And C is 1 over 30 in this arrangement. And so now I see addition very prevalent here. So I'm going to break this across into 3 inverse Laplaces. I'm also going to take out the constant multiples. So I get negative 16 over 5 times the inverse Laplace of 1 over s minus 1 plus 25 over 6 times the inverse Laplace of 1 over s minus 2 plus 1 over 30 times the inverse Laplace of 1 over s plus 4. And I pulled out all the constants here. Because each of these are relatively straightforward in terms of the function in t space, whose Laplace is this. 1 over s minus 1, well, the function that gave me that had to be e to the 1t. 1 over s minus 2, the function that gave me that had to be e to the 2t. And 1 over s plus 4, the function that gave me that had to be e to the negative 4t. So, and there it is. There is the function whose Laplace transform is this. Let's remind ourselves that the Laplace transform of the derivative of a function is s times the Laplace of that function minus our initial value. The Laplace of a second derivative, we worked this out last time, is s squared times the Laplace of our function minus s times our function evaluated at 0 minus the derivative of our function at 0. We could conceivably be curious as to what is the Laplace transform of the third derivative of a function. And we treat this just like we did with the second derivative the other day. Treat this as the derivative of y double prime. And so we get s times the Laplace of y double prime minus y double prime at 0. Continuing to step back, treat this as the Laplace of the derivative of y. This becomes s times s Laplace of y dot minus y dot at 0 minus y double dot at 0. One more Laplace of y dot to do. We get s times s Laplace of y minus y of 0 minus y dot of 0 minus y double dot at 0. And distributing all of this through, we get s cubed Laplace of y minus s squared y at 0 minus s y prime at 0 minus y double prime at 0. And we can imagine arbitrarily extending this into whatever dimension we want, or however many high derivatives we wanted to. We could do the 50th derivative of y if we wanted to. I'm not really sure why we would want to, but we could. So again, the fun in this class comes not necessarily in the esoteric transformation, but in how does this help us solve differential equations? So let's look at a differential equation that we already know how to solve. Indeed, we perhaps have solved this numerous times before. Let's say we have this first order differential equation. It is inhomogeneous, but we know how to solve this using current techniques. Right, we could break this into homogeneous and inhomogeneous. Homogeneous characteristic equation is r plus 3, giving us an r value of -3. The inhomogeneous portion of this is we would use a guess that it looks like a sine of 2t plus b cosine 2t, and then find the values of a and b, which make that true. But let's look at this through the lens of Laplace transforms. First thing I'm going to do is take the Laplace transform of both sides here. So I have the Laplace transform of y dot plus the Laplace transform of 3y is equal to 13 times the Laplace transform of sine of 2t. The Laplace of y dot is s Laplace of y minus 6, the initial condition, plus 3 Laplace of y. That's equal to the Laplace of sine of 2t is 2 over s squared plus 4. And so solving this for the Laplace of y, we have, well, let's go ahead and just factor out the s plus 3. S plus 3 times the Laplace of y is equal to 26 over s squared plus 4 plus 6. Which means that the Laplace of y being the solution to this differential equation, the Laplace of y here is equal to 26 over s squared plus 4 times s plus 3, dividing both sides by s plus 3, plus 6 over s plus 3. And so y then would be the inverse Laplace, the function whose Laplace transform is 26 over. Let's go ahead and combine this so that it's a single fraction. Multiply this by s squared plus 4 over s squared plus 4. I get 6s squared plus 24 plus 26, so plus 50. Over s squared plus 4, s plus 3. And so if we could find a function whose Laplace transform was this, we could find a function whose Laplace transform was this, we would have our solution here. Oh, and that's like, well, that's what we've been focusing on, right? We've been looking to identify, based on patterns, what are the functions whose Laplace transforms are this? Well, again, I've got a quadratic times a linear in the denominator. So I'm going to do partial fraction decomposition, break that apart. Since this is a proper fraction, we can get away with that. And then find the constants a and b, possibly c, and make that work. Let's do one more example. So say we have a more complicated function, y double dot minus 3y dot, or more complicated differential equation, plus 2y equals e to the negative 4t, subject to the initial condition that y of 0 equals 1 and y dot of 0 is equal to 5. I want to find the solution to this differential equation using Laplace transforms. Again, we don't need Laplace transforms to do this, but we can cut our teeth on functions we already know how to do before we get into the more interesting functions, or the functions that sort of defy our previous approaches. So I'm going to take the Laplace transform on both sides here. So I have the Laplace of y double dot minus 3 Laplace of y dot plus 2 Laplace of y is equal to the Laplace of e to the negative 4t. The Laplace of y double dot is s squared Laplace of y minus s times our initial value, 1, minus five. And then this is minus 3 times, now the Laplace of y dot is s Laplace of y minus 1 plus 2 Laplace of y. We already know the Laplace of e to the negative 4t is 1 over s plus 4. Let's clean this up. On the left, I'm going to keep everything with the Laplace of y on the left and factor it out. So I've got s squared minus 3s plus 2 Laplace of y is equal to 1 over s plus 4 plus s plus 2. Dividing both sides by s squared minus 3s plus 2, I get that the Laplace transform of the y, the solution to this differential equation, is 1 over s plus 4 plus s plus 2 divided by s squared minus 3s plus 2. And this is perhaps the least helpful way to write this. So I'm going to take a minute and clean this algebra up, find a common denominator among these three terms, combine those, and then divide by this. I'll go ahead and factor the denominator. And I get that this is s squared plus 6s plus 9 over s minus 2, s minus 1, s plus 4. So y, the solution to this differential equation with these initial conditions, has a Laplace transform of this. So if I could find some way to undo that Laplace transform, to find the inverse Laplace, if you will, of s squared plus 6s plus 9 over s minus 1, s minus 2, s plus 4, then I would have the solution to this differential equation. I would have been able to solve this differential equation problem doing nothing more complicated than some basic algebra. This is problematic, though. I've got quadratic in the numerator, cubic in the denominator. It's a proper fraction. We can do partial fraction decomposition on this, and in fact, we've already done that. This is the inverse Laplace of negative 16 over 5 over s minus 1 plus 25 over 6 over s minus 2 plus 1 over 30 s plus 4, which means that this is negative 16 over 5 e to the t plus 25 over 6 e to the 2t plus 1/30 e to the negative 4t. Quick check to make sure this makes sense based on our current understanding. Maybe we've just gone totally off the rails. Looking at this differential equation, the homogeneous portion, if I had solved the homogeneous portion using a characteristic equation, this would have been r squared minus 3r plus 2, which factors into r minus 2, r minus 1. So positive 2 and positive 1, e to the 2t and e to the t. My solution has both of those terms here. Looking at the forcing term, the right-hand side, I ended up with an e to the negative 4t, which means my guess would have been a e to the negative 4t. And look at that. I've got a constant e to the negative 4t. So this at least makes sense given the problem. To check to see, to make sure this is correct, I can take the second derivative, take the first, I can take the first derivative, take the second derivative, do the second derivative minus 3 of the first derivative plus 2 of the function itself. And if I get e to the negative 4t when I do that, then I have a solution to the differential equation. One last thing I'm going to leave us with is a definition. And what I'm going to define here is a piecewise function which is defined as being 0 or 1, depending on the t value. It's going to be 0 to the left of some a value and 1 to the right of some a value. We are defining this function. So henceforth, when you see cap script u t minus a, you know that is this particular function, which begins as being off and then switches on at some a value. Alternatively, you might see this called, for conciseness, you might see it cap script u sub a of t. You might also see this as h of t minus a. You might also see this as h sub a of t. These are all interchangeable ways of referring to this exact same function. This function is called the Heaviside function. And we like the Heaviside function because it gives us a way to describe something which changes behavior at some value. Call it a. So we might be asked to write some other piecewise function as a Heaviside function. So say we have f of x begins at 0 until time 3, and then it switches on to take on a value of 5. Well, then we could just write this as, if it was just 1 here instead of 5, then I could just call that, well, that is literally just cap script u sub 3 of t. Unfortunately, this takes on a value of 5, so I need something which is 5 times larger than that. Well, I can just multiply the Heaviside function by 5. We might have f of t is starting at 20t and then switches off at 7. Well, in this case, I need it to start at 20t, and then I need it to be 0 when the Heaviside function is switched on. The Heaviside function switches on at 7, so I just now need to have something when this is 1 is going to 0 out the 20t. Well, the easiest way to get rid of a 20t is to subtract 20t. And so here we have this piecewise function written as some combination of the Heaviside function. And for giggles, let's find the Laplace transform of the Heaviside function, the generic Heaviside function. Now remember, the Heaviside function is 0 until time a, and then it switches on. We don't have any patterns we can go back to here, so we just have to break this down to, well, what is the definition of a Laplace transform? This is 0 to infinity of e to the negative st. Now I've got the Heaviside function in here. And just like any other time we're doing integrals with a function that changes behavior, I'm just going to break this into the intervals of its behavior. This is 0 to a of e to the negative st. Now on 0 to a, the Heaviside function takes on a value of 0 because it doesn't switch on until it gets to a. So now we have a to infinity of e to the negative st. The Heaviside, when it's switched on, takes on a value of 1. Now this is a definite integral of 0. The area under the curve y equals 0 is 0. So now I'm left with this one. Well, this is negative 1 over s e to the negative st, evaluated from a to infinity. Pretending that this is a proper integral and I'm allowed to to do this here. This really should be a to b, where the limit is b goes to infinity, but we'll pretend that we all know that. So what I get here is 1 over s e to the negative a s, which is interesting, because this is the first time we've seen this exponential appear in Laplace space. That's where we'll call it today. When we come back, we will continue to explore how Laplace transforms and the Heaviside functions can inform our ability or enhance our ability to solve differential equations.